Welcome to another video from Optatube. Today, we're diving deep into nuclear power, but probably not in the way you're expecting. We're going to pull back the curtain on how this absolute powerhouse has managed in the super complex world of grid modeling. So let's jump right in.
All right, so this right here, this is the central puzzle. I mean, you've got this incredible, powerful, totally carbon-free source of energy. It's everything we want, right? But when it comes to the daily grind of scheduling the power grid, these massive plants are, well, surprisingly stiff. They're just not flexible. So what's the deal? Why can't this giant be a little more agile?
So the answer really begins with the technology itself. You gotta understand, a nuclear plant is not like a natural gas plant that you can just fire up in a few minutes. Nope. Its inflexibility is basically baked right into its DNA, both in its physical design and, as we'll see, its economics. And this list here really lays out the core problem. The upfront costs to build and maintain one of these plants are just astronomical. But the fuel, the stuff that actually makes the power, it's dirt cheap. Because of that, these plants are engineered to do one thing really, really well: run at a steady, constant output 24/7. Trying to shut them down or even just turn the dial down on the power is a super slow, super expensive, and technically tricky business.
Okay, to really get this, we need to talk about a key concept called the ramp rate. Just think of it like a car's acceleration. It's how quickly a power plant can step on the gas or hit the brakes on producing electricity. Now, for some power plants, this is lightning fast, but for nuclear, yeah, not so much.
In this chart, it shows you the problem perfectly. Look at this. To go from its minimum power level to a higher one, this nuclear unit is taking hours. Now think about it. Grid demand can shoot up in a matter of minutes. So that really slow, deliberate pace, that's a huge operational headache. And it's not just about the speed. It's also about commitment. Once you make the decision to turn a nuclear plant on, it has to stay running for a long, long time. Same thing if you turn it off. It has to stay off. You just can't flip a switch for an hour to cover a quick dip in demand. It doesn't work that way.
All right, so we've got these major technical hurdles. But believe me, the story does not end there. The economics of a nuclear plant are just as crucial for understanding why it's so inflexible. So let's follow the money.
This comparison here really spells it out. For a nuclear plant, almost all the cost is fixed. Think of it like the mortgage on the building, the staff salaries, the security, all that stuff you pay for no matter what. The actual fuel, the variable cost, is just a tiny fraction. Now flip that for a gas or coal plant, where the fuel is a much bigger slice of the pie. So in the world of grid modeling, this all gets boiled down to a pretty simple formula. The total cost, let's call it C of P, is just A plus B times P. So A is that giant fixed cost you have to pay no matter what, and B is that teeny tiny extra cost for every single megawatt hour of power P that you generate. And this graph is the result. Because that B value, the cost of fuel, is so incredibly low, the total cost curve is almost a flat line. What does that mean? It means it costs pretty much the same to run the plant at full blast as it does at its minimum setting. So from a purely economic point of view, why on earth would you ever turn it down?
Okay, so we've got the physics and we've got the economics. Now, the real trick for a grid modeler is to take all of these real-world quirks and translate them into a language a computer can actually understand: math. So let's see exactly how they pull that off.
So what the modelers do is translate this reality into 4 key sets of rules, or what we call constraints. You can just think of these constraints as the walls of a box that define exactly how the nuclear plant is allowed to behave inside the computer simulation. First up, we've got the real basics, the operating limits. This is simple. The power output has to stay somewhere between a specific minimum and a specific maximum. I mean, a plant can't produce zero power while it's technically online, and of course it can't go beyond what it was built for. Next, the model has to enforce those slow ramp rates we talked about. So it includes a rule that literally stops the power output from changing too much from one hour to the next. This is what mathematically locks in that slow, kind of turtle-like acceleration. So let's recap. We have all these complex, really rigid constraints, right? We've got massive fixed costs, super slow ramp rates, long commitment times. So given all of that, how in the world do grid planners make this work? How do they fit this inflexible piece into the puzzle to make sure our lights stay on reliably and affordably? Well, The solution, believe it or not, boils down to one simple but really powerful concept: must run. Because shutting down a nuclear plant is such a financial and technical headache, modelers take the path of least resistance. They just label it a must-run unit. The model is basically told, listen, this plant is on, it's going to be running, period. Your job is to plan everything else around it. And just like that, it becomes the solid bedrock of stable, baseload power that all the other, more flexible plants can build upon. And that right there is how the grid squares the circle. This whole modeling approach takes nuclear's biggest weakness, that inflexibility, and cleverly turns it into its absolute greatest strength: unwavering, rock-solid reliability. All right, so let's pull back and look at the big picture. We'll go over our final takeaways and see how this all clicks together.
Okay, so let's wrap this up. First, nuclear gives us that steady, carbon-free foundation for the entire grid. Its inflexibility, as we saw, comes from both its physical design and its really unique cost structure. So in the grid models, this is all simplified by just treating them as must-run units. And really, it's a classic engineering trade-off, isn't it? You accept those massive upfront costs and a serious lack of flexibility, and in exchange, you get incredibly cheap, super reliable, and clean power that pushes more expensive generators off the system.
And all of this leaves us with one final and really critical question to chew on. As our grid keeps evolving, with more and more renewables like solar and wind coming online, what is the future for these inflexible giants? Where do they fit in? That is the billion-dollar question that grid planners are wrestling with right now. Now, if you are interested in energy market and power system modeling and you want updates and insights about the global energy market, make sure to follow the Optatube YouTube channel. Thanks so much for watching.